Hello, welcome to the next of our video series on datasheets and specifying for applications. I'm Kate, Applications Engineer at HEPCO. Today we'll be looking at identifying different loads in an example application. The load capacity and life of a product will be determined by several factors, including the loads that will be seen during use. Once these loads have been identified, we can perform a life calculation to check the life of a unit meets the customer's requirements. When we assess an application, we break down loads into their component form. We can then check the application will operate within the capacity of the unit being specified. In each of our catalogues, there is a page which details the load capacities for that product. These capacities are broken down into direct loads L1 and L2 and moment loads M, MS and MV, as shown in this example from our DLS catalogue. Once we have determined the loads in an application, we use them to calculate a load factor. This is a relationship between the applied load and the load capacity of the unit. The load factor is used to calculate a theoretical life for the unit. Any structure can be subjected to static and dynamic loads. When we look at an application, we are interested in the loads seen as the system is moving, the dynamic loads. We do not, in general, consider the loads seen when the system is stationary. However, in cases where loads are high, we do check these are within the capacity of the unit being specified. Let's look at identifying the loads in a simple XZ application. This is a pick-and-place arrangement with a gripper mounted to a vertical axis. A carriage plate joins the Z-axis to the X-axis, providing horizontal movement. Each axis is driven by a small motorised pinion on a rack. In this application, the axes move independently. The X-axis is stationary when the Z-axis is moving, and vice versa. We can therefore approach each axis in isolation to identify the loads that are present. Starting with the X-axis, we can identify the loads that act on the bearings that carry the plate on which the Z-axis is mounted. The total mass of components carried by the X-axis, including those on the Z-axis, is 8.3 kilograms. To identify the types of loads seen, we need to know the position of the centre of this mass. What we are interested to know is where the centre of mass is in relation to the bearings. In this case, the centre of mass is offset 85 mm to the front of the carriage and 50 mm to the side of the carriage centre line. As with any application, gravity is a constant. It is present when the carriage is stationary and as it moves. Whenever a calculation involves gravity, we use a value of 10 meters per second squared. Whilst the specific value of gravity is 9.81 meters per second squared, a value of 10 meters per second squared is acceptable for use in most situations. It simplifies calculations and is a rounded up figure for the original value. The load resulting from gravity acts downwards on the carriage and applies an L2 direct load. This is a product of mass and gravity and is equal to 83 newtons. Wherever the position of a load is offset from the centre of an object, it will apply a moment to that object. The moment is equal to force times distance and occurs at the same time as the L2 direct load. The offset to the front of the carriage results in an MS moment of 7.06 Newton meters. The offset to the side of the carriage results in an MV moment. Again, this is a product of the load and the offset distance, and is equal to 4.15 Newton meters. Whilst gravity is a constant in this application, there will be additional forces resulting from the movement of the carriage. Typically, these would be seen during periods of acceleration and deceleration. In a majority of the applications we see, the rate of acceleration and deceleration is relatively low. Therefore, the forces resulting from acceleration and deceleration are also low. Additionally, these forces occur for a short period of the total time the carriage is moving. In the life of the application, they make up a small portion of the load seen by the product. For this reason, we can often discount the forces that result from periods of acceleration and deceleration. In applications where the rates of acceleration and deceleration are high, it is worth checking we are within the capacity of the unit during these periods. High rates of acceleration and deceleration may have a negative impact on the life of a system. It is therefore essential that we know the rates of acceleration and deceleration in a system, so that we can accommodate this in our life calculation, if necessary. Now that we have identified the loads on the x-axis, we can input data into our datasheet. The left-hand column on our GV3, SL2 and HDS2 datasheet is for information relating to an x-axis. We can now move on to identify the loads on the z-axis of the system. We can take the same approach we used for the x-axis, identifying the loads seen as the axis is moving. The slides on the z-axis are parallel to the direction in which gravity acts. This means no force is applied to the bearings as a result of gravity. However, there will be a force applied to the pinion where it makes contact with the rack. The pinion supports the full mass of the z-axis, so we need to check the magnitude of this load. The highest loads on the pinion will be seen during acceleration and deceleration. This load is a combination of the force required to overcome gravity and raise the carriage, the force to accelerate the carriage along the slide, and the force to overcome resistance to movement as a result of friction. Whilst the system only accelerates and decelerates for short periods of time, we need to check this maximum load does not exceed the capacity of the gear and pinion. With this maximum load, we can establish whether there is sufficient life capacity in the rack and pinion for the application. We have identified there are no direct loads seen by the bearings on the z-axis, but there is a direct load on the pinion. Something to note in this application is the position of the pinion that drives the carriage. As this is offset to the side of the carriage, a moment will be applied as the carriage is driven. This moment is a product of the magnitude of the driving force and the offset distance from the centre of the carriage. In this case, it applies an MV moment. The total mass of components on the z-axis is 2 kilograms. The centre of mass of these components is offset 50 millimeters to the front of the carriage and is central on the vertical and horizontal axes of the z-axis. There are no MS or MV moments resulting from the offset of the centre of mass. As a result of the offset to the front of the carriage, there will, however, be an M moment. This is a product of mass, gravity, and the offset distance. Having identified the loads present on the z-axis, we can now complete the datasheet, as we did for the x-axis. Once the loads in an application have been identified, it will be possible to make an initial selection of a product and to check this product is suitable for the application. This is done by first checking the loads are within the capacity of the unit and then performing a life calculation. This concludes our video on identifying loads. We hope it provides a firm basis on which to assess your application before completing one of our data sheets.